So, good afternoon, everyone, and welcome to the Center for Automotive Research. My name is Giorgio Rizzoni. I'm a professor in the Department of Mechanical and Aerospace Engineering, and I've done work on things related to cars and trucks and things that go, including buses, for my entire life. We are very fortunate to have an extremely talented group of people here. We run a seminar almost every week during the academic year. And today it's a special pleasure to be able to introduce my colleague, Professor Mark McCord. We've known each other for a few years. And he is the one who's going to introduce the seminar speaker because it is a great pleasure for us to have a group of transportation engineers.
Thanks, Giorgio. Hello, everyone. As Giorgio said, I'm Professor Mark McCord, Professor of Civil Engineering here at OSU. My pleasure to introduce Professor Hong Lo in the seminar today. Before I do that, let me thank Professor Rizzoni and Dr. here for arranging the seminar and inviting Hong to be able to speak today and also for making all the arrangements. I've had interactions with Giorgio and Carl over all the years, and Hong with a couple of his colleagues at PhD organized a reunion of PhD students from the Civil Engineering Transportation Systems group that are back today. We also had a workshop. And I thought it would be a nice opportunity since Hong was on campus to sort of have this seminar over here. And I really appreciate the opportunity. Hong Lo is Dean of Engineering and Chair Professor of Civil and Environmental Engineering and the Director of the Great Smart Cities Institute at the Hong Kong University of Science and Technology. His expertise includes smart cities, dynamic transportation systems, public transportation analysis. He's the founding editor-in-chief of Transport Dynamics, managing editor of the Journal of Intelligent Transportation Systems. He was awarded the Triennial World Conference on Transportation Research Prize. He's a fellow of the Chartered Institute of Logistics and Transport, et cetera, et cetera, et cetera. On a more personal note, Hong was one of my earliest PhD advisees, graduating in 1991. He and I were looking at moving ships through ocean currents that were derived from what that time was new satellite activity data. And even though I haven't really done anything much after Hong graduated, I didn't know how to keep it going. He should have made it go. The idea of using remote sensing in transportation that we started back then has influenced just about everything I've done to this day and continue to do now. And I don't think Hong probably did any ocean routing after he graduated either. I do ferry. He does ferry. And I like to think that the humble beginnings that we started back then with routing ships through ocean currents has led to this productive, pretty good career. So I give you a hug. Thank you.
Thank you very much for the very warm introduction. It's 4 a.m. in the morning for me. We're not going to map, okay? Just talk about concepts, the equation there. If you ask me, I wake up and that's it. So what I trying to say is this is Hong Kong. We're back to normal. If you have not been to Hong Kong, this is basically the city center. So on the tallest building in Asia at that time. This is 19. If you visit me, I take you up to Victoria Peak. This is what you see at night. So it's a fantastic city. This is Hong Kong. For those who have not been there, most people think Hong Kong is very urban. Actually, Hong Kong reserves 75% for hiking. So you can see it's very green. So only this part, which is a green area. So the rest of Hong Kong is all a lot of hiking trails. So very green. 75% reserved for green areas. This is our metro system. So we started metro system in 1978. Now it's very thorough, very comprehensive. So the result is that we also have a lot of double decker buses, which I will talk about. This is a typical scene. You can see there are a lot of double decker buses. All that is a taxi and we have mini buses and so on. So it's a very dynamic, very urban very crowded urban area. Yes.
They have double-decker electric buses?
Yes.
Really?
Yes. We started to import that. It's quite expensive. It's about 6 million Hong Kong divided by 8. That gives the US dollar. 6 million divided by 8. That would be the US dollar. Each bus carry about 110 people. So it's quite a big cost. So this is sort of like a snapshot of Hong Kong. It's very multimodal and also very public transport because 90% of all trips are actually carried by public transport. That translates into 11 million trips daily. So huge volume of public transport trips. Metro system, the MTR requires 45% market share. Buses operated by 4 companies, 700 routes, 5,800 buses, 40% market share. So this is basically all double-decker buses. So it's not uncommon to see double-decker buses everywhere in Hong Kong. We also have a very big fleet of minibuses, 358 routes, about 3,500 minibuses. Each minibus can carry about 19 passengers. So it's not small, like a school bus. Think about it. And we also have a taxis as well. One thing very important when we think about is the financial sustainability. Each mall is private, so they are running on the business. So they are very keen on a fair competition, on routing efficiency as well. That's built in. If you're not efficient with it, it's very simple. So they have to look for a lot of internal efficiency as well as competition across board. So that is a very interesting system. A lot of people did a lot of study on competition, on regulation, on financial sustainability, on regulation, on subsidy. So it's a very rich example for public transport studies. So this is basically where I start. We all know road transport is a big pollutant, and in Hong Kong, the second largest source of air pollution, road transport. Fairly generic, very common for all cities. So transport is a big part. And in the case of Hong Kong, the 5,800 maybe less than 1% of vehicles. We are about 700,000 vehicles. So they are contributed 22%. So it's a huge problem. So it's fair to say that if you want to fix pollution from Hong Kong, you have to fix the buses because that is 22% of pollutants coming from buses alone. So somehow this problem becomes huge. So the question becomes how to fix it. So that was a project we started a long time ago. We were kind of ahead of our time. So how do we fix this 5,800 buses of diesel? They're a huge pollutant. They were purchased over the years from the Euro, the Euro 4, for those who know the standard of pollution. So in Euro, we follow the European standard. So in Euro 2, 3, 4, 5, now 6. So each version is cleaner, but also more expensive. So how do we fix the problem? So this is part of the game plan. And the government look into retrofit. Can we add some sort of catalyst to the diesel buses to clean them up so that they don't pollute as much? We call it the retrofit program. The next one is early retirement. So can I early retire? What it means is that in Hong Kong, each bus legally has a life of 18 years. After 18 years, they have to somehow retire. So the question is, should we early retire them before they reach 18 years? Let them retire. Why? Because of pollution problems, because of fuel efficiency, that the newer buses are more efficient. Can we leverage fuel efficiency and less pollution and make an argument for let's not wait for 18 years. Let's retire them a bit early. So we do some analysis on that. And then we introduce, when we retire them, we introduce the clean energy. It could be electric, it could be the compressed natural gas, it could be hybrid. So what kind of fleet size would make sense when we upgrade our fleet? Okay. And finally, once we have the fleet, we look into routing and scheduling. We all know that electric buses, they don't carry the same range as a diesel buses. So you put constraint into the system. You can think about if a electric bus can run 200 km per day per charge. Then diesel bus is about 350. So you have to buy 2 electric buses to replace 1 diesel, right? So pricing wise, it doesn't make sense. It's too expensive. So the question is, as we gradually phase in electric buses, how do we do that? So that we have a mixture of diesel, electric, hybrid, CNG to make it work so that the whole system become efficient. So that is the problem that we are facing and we want to solve the problem. How do we optimize a mixed energy sources so that the whole system become economically viable and in terms of pollution, it's a load. So that is a question that we want to look. So this is a framework for a project, somehow got funding. So it's a quite elaborate project. So you can think about in Hong Kong, because it's all privately driven, you think about the operator profit as a bottom line. I mean, they can do well to society for only so long, so far, right? At the end of the day, the bottom line is that to make money. So the government, of course, want to regulate the system. Now, in the case where it doesn't make financial sense, perhaps subsidy can be as a way to ignite the system so that they stop changing buses, or we can charge emission. So carrot and stick, we go carrot and stick, force them to change with subsidy. You don't charge it for emission. So carrot and stick approach. But travelers, of course, worry about their travel time convenience. You need to change transfer many times. There's a certain scheduling routing may force people to transfer instead of go direct over the door. So the passengers are thinking about what about the fare? If I'm going to upgrade to electric buses, who's going to pay for the buses? The electric bus is about double the price of a regular diesel. So you're not going to charge me for the buses. Why? Emission is not my fault. I just want travel. Emission is the company's fault. It's a government's fault. We call this externality. So externality kicks in and says, why should I pay for electric buses? So all sorts of questions will pop up into how do I make the system viable in the long run, and the passengers are happy. That is, they don't pay for the full cost of converting to electric buses. The government is happy to achieve. We set the goal of 2050 carbon neutrality. So in Hong Kong, so it's a very aggressive goal. So how to achieve it? And operators are okay to making enough as a private company. So those are the 3 constraints that we look at. So we look at first. We first look in the single but fleet management, meaning that I'm only going to replace diesel with newer diesel. That's an easy step. I don't do rerouting because it's the same diesel buses. Now the second step is I'm going to introduce mixed energy types of buses. So we're going to mix bus fleet management. Now in the first step, we do frequency basis. For those in public transport, there are 2 different analysis. One is frequency based, one is schedule based. Frequency based is more like frequency per hour without exact time when you're going to depart, when you're going to arrive. And then the next step is move up into schedule based. I want to know exactly when the bus will arrive and go. So the time is explicitly captured. And why we do this? Because we want to do the charging. And it's very sensitive to the miles and time. So we want to capture the time, how long the bus have been in use. So we know exactly the charging need, while and route, and where to put the charging stations. So the first step is to build a schedule-based multi-vehicle type, multi-vehicle charging. Very elaborate. Don't ask me about the mechanics now. Okay. I'll show you and move on. The next thing, final thing is that now the range is subject to uncertainty. Temperature, loading, the AC turn on, the uphill, downhill, they all change the battery. So how do we build in uncertainty in the battery usage so that I can hedge against uncertainty in such a way when I design the system, I know that some kind of battery, how do I handle this all? So this is like progressing from the more simple to the final step. So you can see that the modeling become more and more complicated and then we have to do a lot of heuristic to solve the problem. So those are 4 steps that the first step. For those who are interested, sure. So single diesel bus split, it's all easy because I'm not going to be routing. I simply ask a question. Given the current bus fleet, given the current, what kind of subsidy will we require if I want to upgrade this fleet? Or do I need subsidy from the government? And the product itself be maintained as I upgrade your bus fleet. So that's the first. So you're going to maximize the total net benefit within the planning horizon. So this is a graph. We call this a remaining life additional benefit cost analysis. So this is a current bus here. In 18 years, no matter what, bus company to replace it a default replacement. So they last only for 18 years. And we will sell the old bus to less developed countries, as Hong Kong, salvage like tobacco to maybe, I don't know where, to Bangladesh, India, to somewhere. The bus is still useful. It's just the Hong Kong government dictate regularly. No bus in Hong Kong shall be older than 18 years. So that is a default scheme. And then so if we see there's benefit, maybe we want to replace the bus earlier by a newer type. Why? Because we can gain on fuel consumption, we can cut back on emission, which we can gain a term called external health costs. So we have estimated each kilogram of emission, what kind of health impact. So we have those econometric numbers. By cutting back on emission, we cut back on health costs, save the hospital costs. So the government can actually gain from the hospital health costs. So that's the argument. So, so we want to strike a balance in terms of early retiring them, so that we reduce emission, so we gain in external cost in health system. Of course, we trade against the cost of upgrading before their life, before their 18 years. So this is basically doing the accounting. So we look into emission reduction per year of the new bus, external cost, mentioned about this, basic per kilogram emission, what kind of health cost the system will gain or incur. This is a remaining life of the old bus. We have to do interest rate discounting back to the present value. And then this retrofit cost. What if I add a catalyst to clean up the emission? So you can do either retrofit or early retirement. So this is the additional cost. You're going to lose residual value of the bus. It's still basically operation. You just don't want it. So you lose the value of that. You also have to pay for the price difference of the old bus versus the new version of buses, and also the cost difference in operation. Typically, this is a gain because the new bus is more efficient. And then this is a retrofit. So we send it to some optimization, which is in my favor. So we optimize the system over time, over the 20-year time span of the bus company. There are two perspectives. One is societal perspective. What if we only want to minimize the external cost of health and also the operation cost? This is the societal perspective. So if government were to run it, this is what they would do. Scheme A. Scheme B will be from the operator perspective. They want to minimize the cost of early retirement and retrofit. Does it make financial sense? They gain a little bit in fuel efficiency, save fuel, but they lose on the new bus. So we're looking at schemes. We set it up in the budget constraint, conservation, bus route constraints, and other constraints. And then this is actually a real study. We look at PMP, Kowloon Motor Bus. They operate at the time a huge, about 6,000 buses, diesel. So we work with them to say, how should we help them to replenish or replace the buses so that they can achieve their goal? So it's a very interesting project. So we optimize this whole thing. So they say that this is the fleet, Euro 3, Euro 1, and so on. And this is the year where they should be replaced. So you can see that some of those are before they reach 18 years with early retirement. And then in doing so, this is more like a time dynamic problem over time, minimize it. So you can see that we do this, we have the benefit cost ratio 4. So that actually makes sense for the company to early retire the person. And then the government will subsidize funding. The reason is that they should be paying for the external cost of emission. The argument travelers should not be paying for externality of society. So that we argue that the external cost, once they cover, it will make a lot of sense for the company. So the benefit cost ratio. So actually, you can see that in Hong Kong, there were no more old buses. They simply replaced them with newer buses before their 18-year of life. So this is the first study. It's actually done. How we help a bus company to retire the buses early, and then argue for some subsidy. The government eventually is a win-win. So everybody wins. Bus company win, government save in external costs, pay for it, and then traveler not having to pay for the extra fare. You know, the electric bus is double the cost of normal bus, so they're not paying extra fare for the new buses. So it's a sort of win-win-win situation. So we propose this concept called remaining life, additional benefit cost analysis, and then we argue what kind of government subsidy would make sense. Basic government pay for external costs on health, so that travelers, you and I, we don't have to pay. So this is the first study. Now the next study is a look into the mixed fleet now. Now, if you're going to replace a bus, you don't have to replace a diesel bus or a diesel bus. So you can replace a diesel bus or electric bus or CNG, compressed natural gas bus. So there are many buses you can replace once you retire the bus. So how do we manage this thing? So the first study, we use a frequency base. We don't want to formulate a problem that we cannot solve. In a frequency base, the number of decision variables are small. So yeah, so we going to look into the mixed fleet. Now, because once you put mixed fleet, the range are different. Right? Electric buses are not the same as diesel buses. You cannot simply replace a diesel bus or electric bus because it cannot run. They run the loop. So sooner or later, this electric bus run out of power, right? So you have to somehow think about a way, sometimes we call it interlining. So the bus has to run multiple routes to make sure that it's optimal. So you cannot simply run it like a loop. So replacement create complication because of the range of the different kinds of buses. So we look into that. So we introduce a new concept called new life, additional benefit cost. We not only look into replacing, we look into also adding to the bus fleet. Why we need to add? Because the electric buses have a shorter range. So if you replace the diesel by electric, it's short. Let's say an electric bus can run 200 km, a diesel bus can run 350. So once you replace one by one, you lose 150 km. So you cannot simply replace it. So the juggle, the interlining to make sure that you accommodate recharging and so on electric buses. So we formulate the problem to look into the optimal device, the optimal combinations of things we replace buses over time. So it's quite an interesting problem. So in addition to replacement, we think about new buses. We add to the bus because of the shorter range of electric buses. And then we look into that additional cost, additional benefit, and so on. So we formulate a problem. The only thing added is interlining. How do we reroute the buses so that the whole system will fulfill the range constraints? So this is again external cost. So what we are still achieving is we want to minimize external cost. Of course, we pay for the buses. Now the new element we added is those are extra expense on operation costs, same thing, loss of residual value of the bus replaced, extra cost. So those are similar to before. The only thing added is the routing. How do I route the bits to minimum or maximize the return? Now, in the frequency-based thing, so there are a number of ways to cut the problem. This is a way where you think about a bus can run this kind of loop from A to B, terminal to terminal, and then swing to C to D. And then we put this red part as a recharging time. So we put this part inside. So whenever you run a certain portion of time, you have to stop for this time to charge. And this that heading to the next OP. So we calculate that, and when you're doing that heading, you can recharge. We build in this part into the optimization. So knowing that they do need to recharge. And then now this one, so this is 10 hours. 10 horizon data points. The next thing is that can I simplify the problem by building a multi-period routing? So we chop this thing into 5 hours and 5 hours. Within this, the bus can last for this 5 hours. And then here, recharging. The problem becomes detached. So that we don't have to worry about the recharging within the. So the formulation becomes simple. So this thing is, we treat the electric bus as normal here. So only after 5 hours, we charge them up. And then we do it another 5 hours. So in a way, we decompose the problem into two separate problems without having to worry about charging within. So this is a more simple thing, and we did it. Now, there are a couple of things we should be careful because of for elimination. If you think about a bus, they cannot run like this and all of a sudden jump to the next OD. Somehow they have to, the bus cannot simply jump from 1 to 2. So if there without constraints, to remove this up to 4. This is 4. For the same bus, it cannot happen. We cannot also do this kind of tool. And this is the only thing that makes sense is you go from this OD and swing to this other OD with that heading. So in the network formulation, we create constraints to cut away infeasible or not practical kind of looping inside the network. That took us quite some time to clean up. So make sure that when optimization is finished, everything is sensible and doable. So that's it. So this is the result. So we look into replacement. You can see that most of the vehicles prefer to go to the there's one for CNG, compressed natural gas, because they do need the range of CNG to cover. So the system is saying that whenever you replace old bus, so go to electric, and then only do a small number of compressed natural gas to simply cover. You don't want to go from diesel to diesel. It's not going to help you. So that is the learning. And then if you do that, we look into routing and not routing. Routing will mean that we do this kind of, you can swing from one OD to the next. No routing meaning you keep on doing loop here. AD, keep on running. Most bus systems in the world do this kind of looping. Very simple, without interlining. So you can see that actually the combination of interlining or routing, you can gain about 15%. Very sizable. So one thing is that for bus operation scheduling, this interlining is a very important part of the problem. So you cannot simply say, okay, let's make it simple. So because there's a big benefit to be gained from this here. Okay, so that's important. And we also find the single period routing, which is easier with less variable or preferred than a multi-period routing. So you can do why not just routing multi-period. So this is what we learned. Now then, of course, we did the vehicle routing. We did some of the additional benefit cost analysis, but it does not capture time explicitly. So we cannot capture time-dependent emission. We cannot capture the precise schedule, when to charge, where to charge. So we move to the next step. So this is schedule-based mixed bus result. So this thing we capture the bus explicitly. Departure time for a certain terminal and arrival time zone. So this is we call this a multi-depot vehicle routing program with multiple vehicle types in the massive under range and refueling constraints. So this become a bit hard. We also capture the refueling issue. Do you want to recharge the bus to full load, or do you want to charge half? This is a time constraint, right? Sometime in the whole day, you don't want to charge it in the full. That may take you a few hours. So you only want to charge it to enough. So we look into partial charging within that day. So and then we formulate a mixed engine program. So we know that the solution is globally optimal. And then we solve it for a large scale problem. So this is the setup. So basically what we do is a time space network. This is a terminal space here. This is time here. So this is 7:30. So we track it by half an hour. Inside the circles, this is the energy content of the bus. So as you move from 1 to 2, the energy will drop. So we actually keep track of energy consumption while the bus is moving. So this is an important aspect. We call this a state-oriented network. So you capture both time, location, and energy content. So, and then we, based on the bus routes, we can look in the passenger route. Passenger can only go if there's a bus. So we condition according to solution of the vehicle routes or bus routes. We look into the passenger routes. At the end of the day, we want to look into the passenger performance. I mean, it's not only enough to look in the bus. That is the charging is okay, and then the operation cost is okay. We look into the performance of travelers. So whether your charging schedule is actually helping travelers or not. So we look into two types of network. So on this side is a passenger network where we want to keep track. On this side is a vehicle or bus network. So if you think about a simple case, suppose this is where before the start of the day, this is where you think about where to send the bus. So you can send the first bus to terminal A, and then suppose this first bus will go into terminal B or stop B. You can see the energy content go down one step. It's not full anymore. It's going down because consumption. See it. And the next step is you can go to here with the energy further going down, or you can say go to some other nodes. So keep track of energy consumption. Or you can say the vehicle simply wait at terminal P, so it's a waiting. Or you can say the bus is sent to somewhere a longer time, recharge up. So look into all the possibility of this network. So you can see this is a very big network. So we optimize for all the possible choices for each bus through this network. Either go to one station, wait, or recharging at that station. And then after that, we look into passengers. Skip a view. So we look into how passengers would perform given the vehicle network. And we want to optimize this thing jointly. So the passenger waiting time, travel time will be combined with the operation cost so that we eventually want to drive down. So this is the formulation. Without going into detail. Partially, part A is the vehicle bus operation cost, and part A is the passenger performance. Now, in the case where the bus cannot carry passengers, we also capture lost demand. We receive some passengers because the routing is not good for them, so we penalize it. So that the final solution we take into account of minimizing total loss of the system. And then we go through also the flow conservation, capacity constraint, bus capacity, road capacity, fleet capacity, refilling station constraint. So put all this into this optimization. So the issue behind my work. So we illustrate how this thing will work for a simple network. So we visualize it, look at it, and so it makes sense. So it's a checking. And then we run it for the full network. Okay, so this is a full network for Hong Kong. This size is not entire. Let's say we look into some routes for 12 hours. OD pair, set up refueling stations, 2 of them. So the software, the optimization, find out where the best location to refuel also. And then the schedules and so on. So this is a slide. If we want to go for mixed route scheduling, the fleet size can be a single route scheduling. So you can save fleet size by 20%, by much more effectively use your route. So again, this is a very sizable improvement. Also increase utilization of the bus trailer. So somewhere between 10 to 20% is where you can get if you go for interlining and schedule together and overtime. So this is the summary is to work on the multi-depot vehicle scheduling, multiple vehicle types under range and refueling so solve this problem. Quite a lot of solutions. Hard problems. So that saves some time for questions. So this is the last one. It's also the most interesting as far as research, right? We have research. So we put uncertainty, range uncertainty. So we know the battery cannot always perform up to 100%. So how do I capture uncertainty inside of this? In practice, most bus companies say limit to 80%. So for example, if the bus can run to 100, they say plan for only 160. Assuming 20% is lost. So I only plan for 160. So this 20% is a planning kind of loss. So I don't want the bus to stop somewhere, run out of power. So let's not run to the maximum. Let's run to 80%. So we look into this problem, and can we do better than 80%? So we formulate the problem under range concern. So in this case, it minimizes the expense. It is the idea. So we capture this uncertain range, and then once we do this every step is an extension. So we can also do partial refueling station problem. So everything we did for the last thing, we carry it, but we add range, become a random. That's what we do. So to capture this uncertainty in energy consumption. So we this is same as before. I mentioned this is a time, location, time, energy network, and then this is the passenger network, same as before. But this time, this is same as before. But this time we add the power consumption can be random. Okay, so add this in. So how do I find out the cost of running our battery? So we add a term called ad hoc costs. Whenever the bus run out of power, I need to pick another bus to carry them, right? So that gives you extra cost. So we call this ad hoc cost when the power runs out. So the question is, should I save 20% energy all the time? Or should I use more? And if the energy turn out to be out of power, I pick a bus to get passengers. So I'm trading off between use more of the battery power, not 80%, maybe 90%. And then I'm factor in the fact that whenever out of energy, I have the additional cost at cost. So what I do is formulate a stochastic program, because it's a two-stage stochastic program. So I design the system to handle a energy level, which is to be defined. It's 80%, could be 70, could be 90% roots. So optimize this now, and then I simulate. Once I finish the design, I simulate scenarios. They look into how many times the buses actually run out of power and how much I need to pay to pick up additional passengers. In other words, I'm trading the 80% versus the expected cost of having to pick up strength passengers because the buses run out of power. So I do this kind of trade-off in a formal context. Of course, I need to put everything back in here. Flow conservation, capacity. So we want to find out what level of range reliability is good So we optimize for the total expected cost. So accepted the problem is something solvable. We call this a reliability-based search procedure. We developed about 15 years ago. So I mentioned in a previous workshop, this problem actually can be formally solved as a L-shape method or Bender decomposition. You can solve it like this, but very, very slow. So we look at the problem and then work very hard to say, can I solve the problem without going through the traditional formulation and find a new approach, which is very good for solving large problems. Only have time to talk about this. So this is some information. Let's go to the result. And then we look into real case as to see whether we can gain by factoring in uncertainty in a more explicit way. So, so you can say, I mentioned about 80% is the common standard adopted by the industry. Okay, the problem is, can I do better than this 80%? So you can see actually, this is the benchmark 80%. And then you can see that when I factor in stochastic variation of the power consumption, I can drive it down still further. How much? Not very. But this is based on a small case study. If the power consumption vary a lot, I can see this is basically a very important approach to capture mixed-fleet routing problem under uncertain power consumption. So this is basically for this part. Let me summarize. So this part, if you go back, so there's a substantial benefit to be gained, even for a single. I already replaced your diesel buses. That's the first part. The second part is here. That means if you include vehicle routing plus interlining, there is a substantial benefit. So the formulation becomes more difficult, but you also save a lot. So the work you have, because fuel consumption is the largest part of the bus operator. Other than the driver cost, it's all fuel costs. So 13% is quite big thing. And the third part is this part. When we do schedule based, make it very precise. Telling the bus when to go to what stop instead of like a frequency based, you can still gain further advantage. Pretty cycle, I would say. So it's worth the effort to go into the more elaborate modeling effort. Another 20%. The final step is a stochastic. So you still gain more if you include the model to capture random energy consumption. The difference is not that so big. So it depends on the context. You may not want to look into the detail. There's all this very details. Those are the papers. This is basically one student worked very hard. So they finished the whole series of stuff. And then the method that we developed, actually we are a bit ahead of the time. This few people cited really well. We did it almost 10 years ago. Some of the papers cited over 150, 200 now. So it's a well-cited kind of work. I think the industry and the academia picking up on this. How do I make electric bus as an important component of the public transport system? So let me stop here. Very good. Thank you.
Great overview. A lot of important steps along the line.
Yeah, may I? Fantastic, really fascinating work. As we were talking about, we're doing some related, not the same, but related. But I'm going to add phase 5. Maybe we can work together on phase 5. The additional dimension is that batteries age. So all of your stochastic things are based on a fixed capacity of the battery pack. But over time, and the 18 years worries me. Okay, here in the US is 12 years, the life of the bus. Then they go off somewhere else, and they're still quite good. Okay? So the point is now, imagine that the capacity, which means the range of your bus, changes over time. What do you think?
It's a very important question. It can be factored in.
I think you can work on it.
Exactly. you can factor in the aging, because we do capture year by year by time. So you can capture degradation of the battery. And then you can even add when is a good time to replace it. So that you keep the performance. Because it drop in battery, meaning drop in range. Drop in range meaning you need more buses. So you
You're
just
right.
have to.
Yeah, so the replacement now could become just a battery replacement, not the top piece. But you've got the structure.
Um, thank you, fantastic stuff. Two questions. One, just clarification. Are we talking about the bus having to go back to the depot to charge, or is there opportunistic charging or only specific? Like, so could it charge for 5 minutes while maybe it's on hold to get, in line with the schedule or et cetera? And then I'll ask the second question when you.
This is basically we specify how many charging stations you want, and then it will calculate. So and then you calculate full charge, a quarter charge, or half charge.
But is it off service? Is it out of
You
service?
just wait. You just wait. For example, like
But I
it's
mean,
the inside terminal.
yeah, but it's basically out of service.
Yes.
We don't have passengers on the bus.
No.
Why
It's
not
not
charging?
right.
Okay, got it. So that's not part of the.
No, it's not like while you're moving, it's charging.
Got it. Okay. Is that something that is technologically?
It's true
now
about
or-
the charging. Depends on the roadway.
Mm.
It could be very expensive.
But what about at stops only, not necessarily the entire roadway?
So that's exactly as certain stops you charge. But I understand what you're saying. You make all the terminal.
Yeah.
The pavement.
Yeah.
You charge it. So depends. In the Hong Kong buses, they run very high frequency.
Hmm.
They don't stop there for an hour.
I see. So
They stop there for 5 minutes.
Okay.
They probably
it's not worth it. Yeah.
not worth it.
Yeah. So the other question I have is related to, and again, I'm not sure if I'm curious whether it's even something that might squeeze more out of the system. You could have a lower range bus.
Yes.
So you lower the weight of the battery, so actually carrying the battery is not going to consume as much energy. Of course, you get lower range and you get a cheaper bus. So is that at all a possibility where you can maybe replace one diesel with 3 smaller range buses that are maybe more efficient because you're not carrying a lot of batteries around? Or is that at all?
Yeah, because driver cost is not expensive. The reason why we use double decker is exactly you need one driver for 110. If you make a single decker, you need 2 drivers. And driver salary is important. Yeah. So that's
what drives
the
it.
balance.
Yeah.
Yes. For light demand, I agree. For the US, there's no reason why you need a double decker. The demand is never 110. So you don't need a double decker and to lower the battery. So everything you have to scale with the economy.
Would that difference sort of affect, you think, the relative savings in different formulation?
It can be calculated inside.
It could be.
It depends on demand. Depends on demand pattern. If demand is lower, there's no reason why we drive it. So I don't see ever in Columbus you need a double decker, except for tourists. You want to move the open deck and
Have you looked, I mean, I know there's a lot of research about solar panels to charge batteries or something, but I don't know if it's something that you looked into or that
Yeah.
I know in Hong Kong allows you to have a lot of sun to charge with the panel.
the solar panel is used for some of the buses have solar panel to ease the AC. So when the bus is not moving, solar panel is panel the AC. So it's never enough to really power the bus. It's just too little for the bus. Too little. I think a bus easily carry over 200 kilowatt. Easily 200. And then there's no way PV panel can deliver. For terminal AC, maybe.
I have 2 questions.
Yes.
maybe start with comment and just see the how you answer like 10 years research to 30 minutes presentation.
Yeah.
That's amazing. Yeah, the first question, I think the best like benefit from the research you said is saving of the healthcare cost.
Yes,
How did you come up with that
yes.
assumption?
For those people doing ESG, there are econometric models looking into the external cost of per kilogram of CO. They are published studies. So because they have it enough, and the hospital can do econometric studies, looking in the lung disease kind of curing hospital visits. So there are published studies looking into each type of movement per kg, what kind of external cost that will induce or incur to society. I think UK did a lot of this kind of studies. So, and then we use it as a base to calculate the benefit of emission reduction. So that is basically how we argue for government subsidy.
Awesome. So I have more questions for that one, but I can save for later. The second is continue for the age concept, right? You consider different type of vehicles. Do they have the same like age length and some like maintenance? The
Yes.
battery is one type of maintenance cost, right?
Yes, I think
You goes into your
electric buses are very low on maintenance. Very low. The motor doesn't do. But for diesel, you have to fix it. And then for aging, it's really the battery. That age. For diesel, I don't think it's age as much. It's really about new technology popping up. So the Euro 4, 5, 6 coming out. And then you always want to get to the latest. So it's not really about maintenance much that you want to squeeze fuel efficiency. Remember, the bus are running all the time. If you save 10% fuel, that's a lot.
how about the hybrid?
A hybrid is still a very, I don't know, we look at it, but we have not got any hybrid. The technology for buses are very, it's too new for buses. We put in some numbers, it just didn't work out to be, because in hybrid, you still have emission. So somewhere in the middle is probably not good for buses. You want range, and they don't have as much range. You also have emission. So somehow for buses, unless the technology becomes very different, so it just doesn't cut it. So therefore, it doesn't come up. Yes.
Did you also consider swappable batteries?
That's very popular in China, but the bus battery is so heavy. It's just basically you need to bring in the factory and inject the whole thing. This thing is not quite convenient because you need a very heavy lifting. And then you cannot have many terminals. So this got quick. So for private vehicle, for buses, it's very hard.
As far as I know, for the trucks, the range will be shorter if you swap the battery. The range will be shorter.
And also you need equipment to lift this thing, which is not true.
I have a question about the range uncertainty that you had, like you included that as a random variable.
Yes.
So was it like for each route it is like randomly assigned, or there is some systematic way that it's winter now, so we should be reducing range more than it's in summer? So like has it done like that, or just randomly assigned by?
No, we actually collect data route by route. Look into power consumption, and then you can build a distribution.
Okay.
This is something like passenger loading is important. You cannot always have the same passenger load. And then temperature is important because the AC is running. So there are a lot of random factors that affect that. So all we have is data on the bus route. So we did it route by route.
So
It's not like one for all.
okay, so you had data.
Yes, yes.
And one more question, like from Professor question. Did you have any like for the emissions? You said that you found how much is the societal cost. Like, did you have like air quality because of emissions? Because you have emissions somewhere, but they will get dispersed and then it will have an impact somewhere else. Did you consider that in your models?
We look at basic pipeline, a pipe outside, so we use that as the estimate external cost.
Yeah, but it can have an impact somewhere else as well, like where there might be more density of people that may be more impacted than the total number of emissions that is happening.
That's a good question. Let's say, your province emit a lot to my province. Why should you not pay for mine? In the entire Hong Kong, we just have one, we have one agency, so we are. I know what I mean. So let's say if pollutant dispersed by wind to another county.
Yeah, so maybe we should then focus on more routes that are producing emissions that are then impacting other places. Not like we should have like more priority given to the routes that are producing emissions that are actually causing more harm to society than like looking at the whole picture in one go. Like that is, we don't have to then electrify all the routes. We can just electrify those routes which are causing more harm to the society. That's
I think that can be done with some GIS, but still it's one agency. So what you're saying is that unless you charge, we thought about charging certain routes because of the steep hill and overloading conditions, so you charge them. So one way is subsidizing, is charging. For the bus route using this highly polluting corridor, I'm going to charge you.
Yeah.
Charge you for that. That is not very popular. Of course, charging is always something people hate.
I don't know if they're related to this. The idea, I admit, but the people that are affected, no one's affected with health unless that emission hits people. So it's got like the population density. So what do you do in terms of where that emission, how many people does that affect?
It's very hard to, there's a lot of dispersion of emissions.
yeah.
So you can estimate, but it's just too much.
What do you do in your model?
We just look at pipe. Whatever outside, we charge. So the external costs relate to how much you put out at the pipe, at the
So there's a cost for the
society.
the emission.
Emission.
That's, but it's not really saying how many people are affected.
Yeah, because if some route is
Eventually, government pay for it. And then who get hurt more? The one who get hurt more will get the health benefit going to hospital, right? So you don't pay them because you live in a bus route. I pay you $10 per day to cover your damage. Unless you go for that level of subsidy.
like, my question was like if some route is completely outside of the city going outside, it's not useful for like electrifying that route because it is not gonna affect the society as much. But if a route is inside the city, that should be given more priority and be electrified first.
But you're assuming uniform density of the
It means
population.
just government. Think about taxing, right? I pay more tax because I pay more income, and then you say not fair, and not everyone can use the same tax, right? It's the same. It's one government. So what we are charging or giving out is to the whole society. And then how do I pay back the specific sectors who are damaged more? That's a different kind of question. How do I? Let's say we price exactly the same thing, right? I charge everyone pricing. How do I return the revenue to who? That's the question.
I think the question here is, if the impact is, say, half a kilometer either side of the, bus route, and if the bus route goes through the mountains where there are very few people, as opposed to a bus route that goes through, a high-density residential district, a diesel bus that pollutes to 5 people, as opposed to polluting to 5,000.
So the key is which route should be replaced with electric bus. That may be more sensible than
That
compensate. So we should look at actually the built-in, because optimization look into the minimum cost. The bus route that do not have a lot of pollutant, then they don't get replaced early. So from that angle is covered, right? So if you have because this is optimizing for the planning horizon of all the bus routes, all the buses. So which one you pick to replace first or buy electric buses depends on your pollutants, right? Emission. So when you optimize it, you minimize the total emission.
My idea is different, like you shouldn't be thinking about the tailpipe emission, but the impact of that tailpipe emission on the people. So that's what you should be considering is something is my thought on this rather than the total emissions directly. Because that emissions can happen anywhere. Like if it's very happening outside the city limit, then it's all right. It will be mixed with the environment and concentration. It won't affect the air quality. But something that is happening inside the city limits will be more important and should be identified first.
I agree. So you have to do GIS of the
Yeah.
operating, look into the buffering along the bus routes and which one have more population. I think that can.
That's a culture difference because here we have all kind of bus, only have 3 people running rural area. Hong Kong does not have that problem. They are all serve the dense the population. So it's not like they run through mountain. No, it's for hikers. Sorry, I just want to.
One more question, then we should stop. Okay, but thanks for sticking with us to the end. Thanks for both the civil engineering and the car people being here, Coda people online. Thank you very much. Let's thank Professor Wolf.